Okay, so let's unpack this. We're doing a deep dive into a pretty exciting area, polymer nanocomposites.
Yeah, definitely exciting. Our source material is basically a research overview, takes us through the essentials.
Right, the fundamentals of these advanced materials.
And the core idea is actually, well, pretty simple on the surface. You take everyday polymers, plastics, rubbers, that sort of thing,
Uh,
and you blend them with tiny, really tiny nanostructured fillers.
Fillers like carbon nanotubes, graphene,
Uh-huh.
nanoclays, that kind of thing.
Exactly. Could even be quantum dots. Super small stuff.
And the big goal here, which the source really stresses, is getting materials with like way better properties, often multiple enhanced properties.
Properties the original polymer just wouldn't have by itself.
Yeah. So we're going to look at how this overview says they're actually made and why the structure down at that nano level is so critical.
And, how researchers are trying to engineer them for what's next, for future applications.
So our mission really is pulling out the kind of most fascinating bits from this overview.
And figuring out why things are moving so fast in this field, especially when you look at the practical side.
Okay, so the source material seems to zero in on what? 3 main areas that researchers are focused on.
That's right, 3 key areas, and it really emphasizes that first one, synthesis and processing. That's a big hurdle.
Synthesis and processing, so just how you make them.
Yeah, how do you actually get these diverse nanoparticles, maybe it's nanotubes, maybe graphene, which have amazing properties individually.
Right.
How do you get them into the polymer matrix effectively?
And it's not just like stirring them in a bucket, I guess. The source mentions things like solution blending, melt compounding.
Layer by layer assembly even, lots of techniques.
So what's the really tricky part, according to this overview?
Well, the challenge that keeps coming up in the research is getting uniform dispersion, spreading those nanoparticles out evenly.
Ah, okay, so they don't just clump together.
Exactly. Clumping is bad. And maybe even more important is getting strong bonding or interaction right at that interface, where the nanoparticle meets the polymer.
Right. If they don't stick well or if they bunch up.
Then you basically lose all the benefits you were hoping for. So the source really talks about these processing methods as ways people are trying to fine-tune that arrangement, that interaction at the nanoscale.
Okay, that makes total sense. Get them in evenly, make sure they talk to the polymer properly. So assuming you can do that, what's the next big focus the source points to?
That leads straight into the second area, really understanding the structure property relationships.
Structure properties, so how the way it's built affects how it behaves.
Precisely. And it's not just, academic curiosity. If you deeply understand how that carefully built nanoscale structure controls the material's overall bulk behavior.
Then you can actually design materials deliberately for specific jobs.
Exactly. That's the key to engineering future materials.
So what specific things about the nanoscale structure does the source say matter most?
It mentions things you'd expect, like nanoparticle size, shape, but also aspect ratio.
Aspect ratio, like how long and skinny a particle is.
Yeah, basically. And critically, their surface functionalization.
Ah, so like chemically tweaking the surface.
Right, to help it interact better with the polymer. And then, according to the source, how these particles are distributed matters a lot. Are they just scattered randomly or maybe lined up somehow?
Uh-huh. And that interface behavior we talked about.
Absolutely paramount. It all plays together.
So it's really complex. It's not just which nanoparticle you pick, but every little detail about it and how it sits in the polymer.
And the source makes it clear this whole collective structure is what determines things like, say, mechanical strength or heat resistance.
Electrical conductivity, or how well it blocks gases, maybe for packaging.
Exactly that. And understanding that is the bridge to the third really critical area the source talks about.
Which is?
Engineering multifunctional nanocomposites. This is where it gets, well, really interesting.
Multifunctional. Okay, so materials that can do more than one job at once.
Yes, because the emerging applications, they need materials that perform multiple tasks simultaneously. Integrated capabilities.
The source had some cool examples here, right? What combinations are people working on?
Well, it talks a lot about getting high mechanical strength plus electrical conductivity. Think about using graphene or carbon nanotubes for that.
Right, which you'd need for something like flexible electronics. Needs to bend and carry a signal.
For sure. Or, another combo, transparency plus UV blocking.
Using things like zinc oxide nanoparticles, wasn't it?
That's the one.
Yeah.
Which is obviously key for advanced coatings or maybe sustainable packaging. You want to see inside, but you also need to protect the contents from light damage. extend the shelf life.
Makes sense. Any others?
It also mentions combining thermal stability with biodegradability, using things like cellulose nanocrystals maybe inside biodegradable polymers.
Wow. Okay, and this overview is saying these kinds of multifunctional systems, they're really pivotal, not just lab curiosities.
Oh yeah. Pivotal for sectors like, wearable tech, advanced biomedical devices, better energy storage, and like we said, truly sustainable packaging.
So these could form the basis for actual products you might use every day.
Definitely. It just shows how tweaking materials way down at the nanoscale can open up completely new possibilities, really.
So let's wrap this up. What does all this mean? This deep dive, based on our source material, it shows that by deliberately combining materials at this super tiny scale.
Yeah, at the nanoscale.
We can engineer composites with really specific, desired combinations of properties.
Like you said, strength and conductivity. Or being clear and blocking UV light. Tailor-made materials.
And it's moving fast, isn't it? The source emphasizes it's going from basic research towards real high-performance applications.
Absolutely. In flexible tech, advanced medicine, eco-friendly packaging, it's becoming tangible.
So connecting this to the bigger picture,
Yeah.
It kind of leaves you with a thought, doesn't it? A question to maybe consider. If you look around you right now at the stuff you use, how many of those products could be totally transformed or maybe improved in ways we haven't even thought of by engineering materials at this incredibly small nanoscale level?